start recording this. Okay, well, I'm going to go ahead and get started then. Let me kind of move this over somehow. There we go. I generally don't address anything in the, if you can talk amongst yourselves, and, text us, we get on the, what do you call it? What do you call it when you can put up your little notations, whatever in there. Once I start rolling, it's better I don't get off track because I'm like one of the dogs, squirrel, and I get off topic and then it's hard for me to come back. So, all right. So we are talking about chemistry. We're talking about inorganic and organic chemistry. It looks like a lot, but it's not really. And I've uploaded a sheet. I'll talk about that at the end. I'll try to switch my share to this chemistry chart that I uploaded that I hand wrote out. You're free to use that to help organize this material because it does kind of go on and on and on, and you get a little lost in all the notes as they go, they continue. But, with the exception of maybe the first 10 PowerPoints is that, this chart helps organize at least the organic material, one portion of this. Okay, so matter and energy. Matter is anything that occupies space and has mass. There are three possible states: gas, liquid, or solid. Energy is the ability to do work. We either have stored energy called potential energy, and this is what, how we define the energy stored in bonds that are created, within molecules and between molecules. And then we have kinetic energy, which is the energy of things in motion. So we need to start with the smallest things first, atomic structure. If we were in the classroom, we have periodic tables that list the tables of elements that occur naturally in nature. We have atoms or elements. They're composed of subatomic particles, protons, neutrons, and electrons. Protons carry a positive charge and have mass associated with them. Neutrons have no charge, so protons positive, P to P. Neutrons neutral, N to N. They also have mass associated with them. And electrons have a negative charge and a very insignificant mass. So they're found at different energy levels, or what's called valence shells, radiating away from the nucleus. Things with mass are found in the nucleus. So that's why we find protons and neutrons there. And electrons move around, at different energy levels, radiating away from the nucleus. The atomic number is the number of protons in the nucleus. This will also equal the number of electrons, at least initially, before they start to interact with other elements, maybe, or atoms in their environment. I will tell you that I'm here right now, we're looking at lithium, is that the atomic number for lithium is 3. So we know we at least have 3 protons and 3 electrons before it starts to interact with anybody. All right. So the 3 pluses cancel out the 3 negatives, the electrons, and it's neutral at this point. Generally, it will have probably the same amount of neutrons in the nucleus, but that number can vary. And when it varies like that, it's called an isotope. But it doesn't change the charge because neutrons have no charge. All right, so it's normal in the environment to find different types, so to speak, or isotopes of lithium, hydrogen, carbon, and so forth, because the numbers of neutrons can vary, but their number of protons determine what their atomic number is, and thus it defines it. We would call that, in this case, if we have 3 protons and 3 electrons, we just call that lithium. And if our numbers of electrons change, which can happen, then we become what's called an ion. When it comes to the organization of molecules or atoms, all atoms strive to have their outer valence shell complete. And not that you have to draw these out, but I'll just tell you that the first valence shell can hold up to 2 electrons. And then the second valence shell can hold up to 8. And the third one can also hold up to 8. So as the electrons, become kind of assigned or take up residence in different valence shells, the first 2, not technically, but the first two will occupy the first valence shell. And then the third electron is in the second valence shell. Well, that valence shell is designed to hold 8 electrons, and it only has 1 electron in there. So this is the kind of thing that determines the behavior of lithium with other elements in its environment. More than likely, lithium, hydrogen, right? Sodium is also in that same vertical column to the left-hand side on a table of elements, means that it has only 1, out of all the possible electrons in its outer valence shell. So this is going to kind of make sense. Lithium can either share electrons, right? 7 other electrons from either other lithiums or maybe other elements, that have more or less electrons to share also in its outer valence shell, or steal 7 electrons from maybe hydrogen, let's say, and fill its outer valence shell. Well, that's not very likely, and it just ain't going to happen. Its path of least resistance is going to be to just give away that 1 electron in that outer valence shell. And in doing so, we now only have 3 protons and 2 electrons. And now lithium is no longer neutral overall. It has a positive 1 charge. That's what ions do, or that's how you become an ion. You have certain molecules that because it only has 1 electron, maybe in its outer valence shell, it's just easier to give the darn thing away and be done with it. And it's perfectly happy existing in nature with a positive charge. Chlorine is an example of a molecule or an atom, that only needs one more electron in that second valence shell to completely fill it. And so it has a tendency to steal electrons from small little lithiums and hydrogens because they're willing to give it away, and chlorine is totally willing to take it, right? And that completes its outer valence shell. And therefore, because now it has 1 extra electron than it does protons, it assumes a negative charge or a -1 charge. And so depending on how many electrons are in their outer valence shells will kind of determine what kind of bonds they're more willing to create. The attractive force, the bond is an attractive force between different elements in a molecule. So it may be more likely to give an electron away, steal an electron, or share electrons with other elements in the environment. And that's another factor. What is in the environment? So the degree of, how many electrons are in its outer valence shell, how close is that element to stability? Because once that valence shell is complete, it will not create any other bonds with anybody else, with few exceptions. And I'll give you an example, of the kinds of bonds it can create, but it won't create like an ionic bond, and it will essentially become, what's called inert. It'll act like a noble gas, which are the elements to the far right-hand side vertical column of a table of elements. But while we have this picture up here, it's just a good way to, a good example to see a molecule that has, only 1 out of the 8 electrons, in its outer valence shell, and that generally the path it's going to follow to, become, rather chemically inert. It's just going to give that electron away. All right. So this chart, and generally when I make you charts, it's usually good to maybe practice them a little bit, drawing them out and committing them to memory, because if I go through the trouble of making a chart, I generally ask at least 1 or 2 questions from it. All right. So this on the top compares mass and charge with protons, neutrons, and electrons. Right? So maybe next to a proton, maybe just draw in there a positive charge. So you remember it's a positive charge. Next to a neutron, just put a 0 because it's neutral. And an electron, maybe a negative next to it. So which ones have mass? Protons and neutrons, and that's why they're found in the nucleus. Electrons have minimal mass. The charge associated with them, protons are positive, neutrons are neutral, and electrons have a negative charge. So, some questions are just as easy as that. Which subatomic particle has no charge whatsoever? Which subatomic particles are found in the nucleus? Things like that. Okay, so here we're looking at the distribution, and where we find protons and electrons. In hydrogen, which is an atomic number of 1, the atomic number is the number of protons. And again, at the beginning, before it starts creating bonds, then it also has the same number of electrons. Helium is an atomic number of 2, so it has 2 protons in the nucleus and 2 electrons. And now that is inert, right? That has reached what I call chemical nirvana, right? It's filled its outer valence shell. It is one of the noble gases, the first noble gas in the vertical column to the right-hand side of your table of elements. And then again, we have lithium. So 3 protons, 3 electrons, 3 protons in the center. First 2 electrons fill the first valence shell. The third electron goes to the next energy level. So not that you're going to have to write them out, just that you kind of appreciate, hey, if this was chlorine and it had 7 out of the 8 electrons in that outer valence shell instead of just the one that lithium has, now you see how, oh, it only needs 1 more electron. It's probably going to try to buddy up to either hydrogen or lithium, maybe even a sodium to take its outer electron, because they're willing to just give it up. The larger they are, and the element, and the closer they are to filling that outer valence shell, makes it a very strong magnet, so to speak, to yank away other electrons, from other elements in its environment. It's called having a very strong electronegativity. And as soon as they get really close to that, they just start, sucking up electrons around them wherever they can. And then they're kind of inert. So electrons and bonds, 8 atoms or elements, are stable if their outer shell, the valence shell, is full. The first valence shell holds 2 electrons, and the next 2 levels each can hold 8 electrons each. Right? Noble gases have a full valence shell and are non-reactive. Electrons will be given away or taken away or shared between atoms to fill their outer valence shell, and this is the basis for forming chemical bonds. And so that's the whole premise of it. They react and they do things on their own. They don't have to be pushed. They don't have to be encouraged. They're just striving for this. Okay, so again, this is just another picture from your textbook. When we have the most outer valence shell complete, like in the example of helium, here's neon. And then over to the right-hand side, we have examples of hydrogen, which only has 1 out of the 2 electrons. Here we have carbon that has 4 and it needs 4 more. Oxygen that has this always 6, so it only forms 2 bonds. So it needs 2 more electrons in its outer valence shell. And sodium has only 1 in its outer valence shell, so it's willing to give that away. And so you can almost, by becoming pretty fluent with the table of elements, which is not required of this course, you write very few chemical reactions, in between AMP1 and AMP2. But if you understand what drives these elements to form the bonds that they do, then you kind of understand a little bit better and it sticks with you a little bit longer. Okay, so bonding of the atoms, ions. So we were just discussing that. We're just saying, some elements, they have only 1 electron in its outer valence shell. So it's very, very likely it's just going to give away that electron. And there's often another element in the environment that really needs only 1 more electron. And so they're more than willing to take it. And a good example of this is when you bring together sodium and chlorine. So sodium is willing to give an electron away, thus it assumes a positive charge because it has 1 less electron, and the chlorine willingly accepts it. And now it has 1 extra electron, so it's a negative charge. So when atoms or elements gain or lose electrons to become stable like this, they're called being an ion. If they end up with a positive charge, we call it a cation because they lost an electron, and that would be a positive 1. And if it gained the electron and becomes more negative because it gained an electron, then we call that being an anion, has a negative charge. If it only accepts 1 electron, then it's -1. If it acquired 2, then it'd be a -2. All right, so sodium is willing to give that electron away. Chlorine is willing to take it. Sodium ends up with maybe less electrons, but a full valence shell, and so does chlorine. And something happened with that diagram because it kind of smushed out some of that. But anyway, so sodium gains stability and so does chlorine by swapping electrons. Now, if we only have sodiums and chlorides, let's say a mole of sodium and a mole of chlorine, and we put them together, they only have each other to swap electrons with. And once sodium becomes positive and chlorine becomes negative, they have the ability to have an attractive force or bond created between the two of them. And that's because opposites attract. So if we only have, let's say, a mole of sodiums and a mole of chlorines, and they exchange electrons, they will form what's called an ionic bond because opposites attract. And they will be attracted to each other and stay there until they have sort of other options. I'll just give you that much right now, and I'll explain that in just a minute. And that's essentially what table salt is. All right, table salt is sodium chloride. And when it only has these other to bind to, it forms these crystals, and they stay bound there until they have, they're put in another environment, either around other elements or maybe put in water or with food, that is very aqueous, and it starts to dissolve. And we'll talk about that phenomena in just a few minutes. Okay, so we are going to look at 4 types of bonds. Bonds are forces that hold atoms or elements together to form molecules or different compounds. So we're going to look at 4 types. We have ionic, polar covalent, nonpolar covalent, and hydrogen. So ionic bonds, it's an attractive force between a cation and an anion. So now how we created, or how a cation and an anion was created, by swapping electrons from one element or atom to another. Formed when electrons are transferred from one atom to another. One becomes positive, one becomes negative, and then look over to the right. This is how sodiums and chlorides will stagger and be attracted to one another. And they'll alternate positive, negative, positive, negative, positive, negative. But we can also have covalent bonds, and there's 2 types of covalent bonds, polar and nonpolar. So covalent means we're sharing electrons. It's not telling you you're sharing them equally or unequally. It just, covalent means to share. So we could have polar covalent bonds or nonpolar. So what does it mean to be polar covalently bonded? It results when electrons are not shared equally, or we have unequal sharing of electrons within the molecule. Water is a great example of a polar covalently bonded, entity. Water, the formula for water is H2O. So we have 2 hydrogens and 1 oxygen. The oxygen is the red, the hydrogens are white here. Now, each hydrogen has 1 electron in its outer valence shell. And oxygen just needs 2 more electrons in its outer valence shell to be complete. All right. So oxygen won't necessarily, steal, or it won't steal the electrons away from those 2 hydrogens, but it's perfectly happy to share. Now, oxygen is much bigger than hydrogen, and it has a larger nucleus, it has more protons, and it has a higher electronegativity, because the closer it gets to filling that outer valence shell, the bigger the magnetic pull it has for those electrons. So the electrons that each hydrogen has in its valence shell, it only has 1, actually get pulled closer to the oxygen end of the molecule. So that end of the molecule, the other end, the end, how can I explain this? The end of the molecule where the oxygens reside more toward, I guess you could say, will have a negative charge associated with it. And the 2 hydrogens will have a positive charge associated with them. They don't give their electrons away. They actually vibrate and hover, and they kind of circulate around the whole molecule, but they spend more time at the other end of of the oxygen molecule than they do at the hydrogens. Not that they don't kind of come back around periodically, but that, generally they spend more time, at the opposing end, the oxygen end. So the oxygen end has a negative charge and the two hydrogens have a positive charge. We have unequal sharing of electrons between the participants in this molecule. And therefore it creates a polarity of charge around the molecule. You have positive ends and negative ends. Water is the most important polar molecule. It's the primary solvent of our body, and so therefore, because of that, when we look at the organic molecules, it'll make sense that most organic molecules will be similarly bonded so that they can be transported and mixed with water, easily. So water is an important polar molecule, as well as amino acids, sugars, the carbohydrate family, and phosphate groups. Nonpolar covalent molecules means that you have equal sharing of electrons. The electrons don't get pulled and reside more at one end of the molecule than the other. So therefore, you do not have a charge distribution, positive and negative ends. It's more neutral around it. Right? So when we have equal sharing, we are considered nonpolar because there's no polarity of charge. The molecules that fall into this family are things like the lipids, the fats, and steroids and cholesterols are in that family. They're all very important nonpolar covalently bonded molecules. All right, so we have ionic bonds, nonpolar covalent bonds, and polar covalent bonds so far. Then we have hydrogen bonds. Hydrogen bonds can be, be sort of defined or categorized as either intermolecular bonds or intramolecular bonds. An example of intermolecular bonds means that the hydrogen bond is between two different, or maybe two similar, identical, polar covalently bonded molecules. And we're going to look at, what happens when we have two or more water molecules, because they're each polar covalently bonded. And we look at, what is the attractive force between one water molecule to another water molecule, to another water molecule, to maybe an amino acid or a polypeptide, because they are going to be polar covalently bonded as well. Right? So those are what's called intermolecular bonds. When we look at how proteins wrap and form what's called the, from after the primary, there's secondary, tertiary, and quaternary structures. That will be an example of an intermolecular bond. Also, within the center of DNA, that is an intermolecular bond as well. So hydrogen bonds up at the top here are a weak attraction between the positive end of maybe one polar covalently bonded molecule to the negative end of another polar covalently bonded molecule. Generally, hydrogen to nitrogen, oxygen, or fluorine is called NOF, N-O-F. But a very good example is water to water, or again, if we talk about intramolecularly within the center of DNA, or what keeps our secondary, tertiary, and quaternary structures of a protein together. So it can be formed between water molecules and through the center of DNA, and then also within the secondary, tertiary, and quaternary bonds of a protein. And that's why we have to look at more detail of proteins and things like that. All right, so those are our four types of bonds: ionic, polar covalent, non-polar covalent, and hydrogen. So here we have, oopsie doodle, here we have 5 different water molecules. So each one, the oxygen is red, the hydrogens are blue, the oxygens are the negative ends, and the hydrogens have the positive ends. So, if you put multiple water molecules together, how are they going to orient themselves with each other? Well, it's sort of like what happened between sodium and chloride with the cations and the anions. Opposites attract. All right, so let's take the one at the top. Here we have the oxygen with the negative end, and the two hydrogens are sticking up, toward the top of the page or superiorly. The negative end of that oxygen will be attracted to the positive hydrogen below it. So negative to positive. And each molecule will do that. the oxygen, the negative oxygen will be attracted to the positive hydrogen, or vice versa, however you want to think of it, and it'll stagger itself as such, just like how the sodiums and chlorides did. Now, when we have, let's say, sodium and chloride, and let's say we put it in water and we put some heat under it to increase, molecular movement and give it a little agitation. And even without the agitation, you just put heat, to the water that you just put some salt in, just plain table salt. You see this when you cook often. Maybe you're going to boil some potatoes or pasta, so you need to bring the water up to a boil, and you're going to salt the water. Well, what do you think is going to happen? You put in the sodium chloride, and the sodium has a positive charge and the chloride has a negative charge. And when they only have each other in their environment, they create these ionic bonds, between each other. But if you put it in water, all of a sudden, sodium and chloride, they have other options. So the sodium that has a positive charge will often dissociate from the chlorine and be attracted to the negative end of an oxygen. And the chlorine that has a negative charge will be attracted to the positive, or one of the positive hydrogens that have a positive charge. And that's how we suspend these different molecules in water. Like dissolves in like, what we refer to. Things that have or substances that have charge associated with them, or have ionic bonds, will dissolve in things that are also polar covalently bonded, like water, right? Because water has charge around the molecule. Sodium and chloride, have charges. Amino acids and sugars, they're all going to have charges as well. They're going to be polar covalently bonded. So, we can dissolve a substance in a solvent, a solute, which is a substance. The solvent is the medium that you're going to put them in. And for our body, for anatomy and physiology, we consider virtually everything water, because that's our primary solvent. So virtually anything with charge associated with it will be able to be dissolved in water. Now, if they're very, very large molecules, they might not be suspended really well, but they might be a little heavy and precipitate out, but at least they're capable of being, suspended. But when you have incompatible bond types, like fats in water, like when you put olive oil in water, or any kind of oil in water, it beads up because you have incompatible bond types. Fats are non-polar covalently bonded, and water is polar covalently bonded. You can dissolve things in oil, other things that are non-polar covalently bonded. So when you have fats and things in the lipid family, they can be dissolved in other fats, because like dissolves in like. So things that are non-polar covalently bonded can be merged and suspended in suspensions, that are non-polar covalently bonded as well. Okay, so these are some. I'm not sure. I think I might have to change my share. I'm going to run one of these, and then we'll try running them both, because they're really cute. So for all you dog lovers, you're going to like this. It's not very long, but it actually is quite good at demonstrating, the relationship of protons and neutrons, in the nucleus, and where the electrons are found. I know I start with, the second of the two, because it talks about protons and electrons. And then the second video is about bond types. Technically, this chemistry instructor named the first video for the bond types, and the second one, the nucleus and protons and electrons. But I just put them in the order in which we were covering them, so that are in the PowerPoints. So let me stop that share, and then I'm going to start this. Hopefully it'll run. There we go. And let me change my share real quick. Hopefully it'll go. Come on. Okay, let me try. I'm going to try to reload that. It might not let me share it anyways. It's not connecting. It did earlier today. We'll try the other one. And Erica, please try again. Maybe too many people are using it. Okay, hold on. Let me close that out. Let me try the next one. Okay, we're going to start that in just a minute. Where is my, there you guys are. All right, let me pull this over. Sorry, it's taking a little bit because the other one. All right, well, this is the second one. Let me move.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching. We'll see you guys next time.
Okay, so let me stop that share before I close that out. Isn't that the cutest thing? Well, the other one is similar in that they talk about, the dogs put protons in a bowl and and then they have their electrons and they orbit around and they chase each other around. It's really cute. So, you can always download this PowerPoint, put it in a slideshow mode like this, and then that will give you an opportunity to watch that other video. I'm not sure what happened with it. It might be because this is, I don't know. I don't know why. I used it this afternoon and it worked just fine. But anyway, so yeah, that's kind of, see, I told you I'm a dogaholic. All right. Someone years ago, this other instructor had found that and she shared it with me and I've always used it ever since then. Okay. So solubility. Solubility is the ability of a molecule called a solute to dissolve in another substance called the solvent. And the solvent is generally more liquid and more expansive, more voluminous. And in our case, it's generally water. That's what we're referring to. And it depends on two major variables, bond type compatibility and molecular size. And that's what I was referring to before. When we were looking at the different water molecules and the attractive forces, the hydrogen bonds that would be between them. Right, so we're saying the water was polar covalently bonded, and hydrogen bonds is the attractive force between the negative end of one water molecule to the positive end of another water molecule, or maybe the positive end of amino acid. Those are all intermolecular hydrogen bonds. And I said that we could put in sodium chloride, salts in there, and as long as you had the same bond type, like dissolves in like, then it would be soluble, up to a certain point, like really well. Things that have high solubility are small molecules. So that would fall into the category of sodium chloride. The building blocks of all our polar covalently bonded organic molecules we're going to look at tonight, proteins and carbohydrates, they have high degrees of solubility. I mean, clearly glucose does, right? Now, although the macromolecules are much longer chains of carbohydrates and proteins and things, and yes, they have the, compatible bond types, they have a lower level or a smaller degree, I guess you could say, of solubility, just because they're so large, compared to the building blocks, the smaller units. But they generally do have solubility. It might just be, moderate or low, but they do dissolve. What won't dissolve or be soluble is when you have incompatible bond types, water and something like molecules in the lipid family. They repel each other. Okay, so then we're going to look at chemical reactions. Chemical reactions occur when chemical bonds form or break among atoms, ions, or molecules. The general categories are either catabolic or anabolic. Catabolism means to break down something, so you're taking a large molecule and you're breaking it down into smaller ones. And anabolism means that you're taking smaller molecules and you're somehow, even if it's just two, linking them together to form a larger one. So, I always think of anabolic steroids, to build up muscle mass. Catabolism means to break down. Anabolism means to build up. Start with small things and put them together for larger ones. And then you need to know the idea of, or the concept of reactants and products. Reactants are what you start with. Products are what you end with. Now, how do you know the difference? The arrow in a chemical reaction always points to the product. It's not because maybe the chemical equation, and let me see if we have another example. I generally do this face to face and write it on the board. But let's say we had an equation, sodium Na plus Cl, and then an arrow pointing to NaCl. That means that we took one sodium, one chloride, and together we made one sodium chloride, one salt molecule. But if I turn the arrow around, and we started with NaCl, and then it pointed to Na for sodium plus a Cl for chlorine or a chloride ion, then it means that we started with one salt molecule and we broke it up into its components, one sodium and one chloride. And that will happen, let's say, if we put that sodium and chloride in water. All right. So you can't always, you have to look at the arrow and what it's pointing to, because that's going to tell you what I'm starting with, what I'm ending with. Am I taking 2 or 3 different things and putting it together to make maybe 2 large things, because that's what the arrow is pointing to, or is the arrow going the opposite direction? All right, so of the chemical reactions, whether it's anabolic or catabolic, we're going to look at these two and the characteristics sort of associated with them. Dehydration synthesis, synthesis means to put together, is an example of an anabolic reaction. Dehydration synthesis requires the removal of at least the equivalent of one water molecule. So we're going to remove water from, let's say, 2 molecules that we want to bind together, right? Bond together. So we remove water, we put these things together, and we store energy in the bond that's created now between these 2, let's say, building blocks, these 2 molecules. When we remove hydrogen from one and an OH group from the other molecule, it opens up an area to create a bond. And that bond, cements them together, so to speak. And in bonds, we store energy. So what does dehydration mean? Remove water, and synthesis means to put together. So this is how we put together, a small molecule and a large molecule, or multiple molecules together to make one, or 2 larger molecules. Right? Dehydration synthesis, remove water, bind them together and store energy, create bonds and store energy in the bonds that are created, maybe. Hydrolysis or hydrolysis is the opposite. This is how we break apart a large molecule into smaller molecules. And it's exactly the opposite of dehydration synthesis. We add the equivalent of one water molecule, we break apart the molecule, break the bond, and we release the energy that was stored in those bonds. And this is how we break down food that we ingest. We have to break it down enzymatically. We have to break it down physically, of course, like chewing and so forth, tumble it around and stir it around, but we also break it down enzymatically. And that facilitates breaking things apart, removing, adding water in this case, and breaking it apart and releasing energy. All right, so this picture gives you an example of what I was trying to say before was depends on which direction the arrow is pointing to. So let's kind of start at the left and move to the right, and then from the right to the left back again. So over on the left, we have an amino acid plus another amino acid. And on the top says, okay, we're going to perform a dehydration synthesis reaction. The arrow begins and goes from the two amino acids to the right to produce a dipeptide. So that is an example of a dehydration synthesis reaction. We remove water, so you can see the little arrow pulling off and, with a little water molecule in blue. We remove water and we create a bond. A peptide bond is a type of polar covalent bond. And now we have a larger molecule and we have energy stored in that bond. But we can also go backwards. We can start with the dipeptide, which is to the bottom, and the arrow now points back to those two amino acids. We're going to put water back into that reaction, and that would be hydrolysis. We break the bond, we add water, and we liberate energy, or we release energy. So you really have to look at the direction of the arrow, because that's telling you whether you have dehydration synthesis or hydrolysis occurring. And then I could give you, another example, and I could say, well, if I started with two amino acids and I ended up, or a multitude of amino acids and I ended with maybe a polypeptide, a really long chain, what kind of reaction was that? Dehydration synthesis. If I started with, a couple amino acids and I ended with a polypeptide, was water added or removed? It was removed. Were bonds created or broken? They were created. Was energy stored or released? So know the features and the characteristics, that go with dehydration synthesis and hydrolysis. They love to ask things like that in lab, I'll just tell you. Okay, so factors that affect reaction rates. Well, enzymes. Enzymes are a type of protein, right? They're a complicated kind of protein, and what they do is they increase the rate of reaction in a chemical reaction by what's called lowering the activation energy. So what enzymes do, and generally, these enzymes are designed to have these binding sites, maybe for two amino acids, maybe two of the same amino acids or two different amino acids, but they'll have these kind of little lock and key binding sites on its surface. And instead of waiting till these two amino acids just randomly collide with one another to, bind them together to form a larger molecule, enzymes, bind, when they're in the environment, one amino acid will bind, dock into one of those binding sites, and then the other amino acid will bind in the other binding site. And now the enzyme, boom, puts them together. It performs that dehydration synthesis reaction. And so you're taking the same amount of reactants, but you're putting them together really quickly. Thus it lowers the activation energy. It lowers the energy that you have to put into this chemical reaction to produce all the products that are desired, and so they speed up reactions, enzymes. The concentration of each of these, the more you have of your reactants, let's say you want to make sodium chlorides. If you only have 10 molecules of sodium, but you have 100 molecules of chloride or chlorine, you can only make 10, sodium chlorides because you only had 10 sodiums. You'll have 90 leftover chlorine or chloride molecules, but you can only make 10 sodium chlorides. So you have to have enough of all your reactants available, to be able to make your final product. So the more you have, to work with, the more product you can make. Size. The smaller, the easier it is to move them around. They have higher molecular movement, and so reactions occur faster. Temperature to a point. When you increase the temperature, it increases your rate of the reaction. It increases molecular movement. Now, one of the problems will be these enzymes because they're proteins. And when we look at the protein family, you're going to learn that the hydrogen bonds that maintain their secondary, tertiary, and quaternary structures are very susceptible to increased temperature, to high temperature and low pH. Technically, high pH as well, but we generally don't have very many instances of high pH values in blood, only really, low pH values in blood or lower. So temperature, yes, you increase molecular movement, but if it goes too high, then you're going to burn up all your enzymes. And now you're slowing yourself down again. Yes, molecular movement is increased and faster, but you've just burned up all your enzymes, and now you took like 2 steps forward and 1 step back, so to speak. So you have to be very careful with that. And then the pH, lower pH means, the lower the pH, the higher the concentration of hydrogen ions, the more likely you denature your enzymes. Virtually every chemical reaction has an optimal temperature and pH for these reactions to occur. And it's the same, there's optimal temperatures and pHs for different bacteria and different areas of our body that, allow it to exist optimally. Let's put it that way. So high temperature and low pH, can risk damaging and affecting your reaction rate. But generally, if it's a moderate temperature, like body temperature, 98.6, or a pH that's about that of blood, 7.35 to 7.45, around that neutral region, then, you're going to be just fine. And so those variables of temperature and pH will kind of come over and over again, especially in AMP2, because when you start looking at normal functioning of, let's say, the respiratory and urinary systems, and then we look at, what can abnormally kind of happen, then you start to go, ooh, well, if it's affecting like body temperature and the pH of blood, we start to get into an area where we can start to, change all our proteins. And I'll just tell you, you can't live very long without your proteins, right? Because they're the molecules that have the most sophisticated, complicated functions in your body. Right? And so if you start to burn those up and break their hydrogen bonds, you're going to be in trouble. Okay, so that takes us to a Kahoot quiz. We can see if this will work. If anybody wants to jump in, I'm going to stop my share and try to reestablish my share. Oh, there it goes. Oh, okay. Let's go in as a guest. Here we go. And I'll click. And then I'm going to quick go back in here, move this around. La, la, la. There we go. Move around. My feet were going to sleep. I'm sitting in my office here, and the air conditioning has not come back on. I think I'm going to lose a few lbs in here. We can change the music. We were using reggae earlier today. Let's see. Oh, yeah. They actually have Christmas music, but I'm not willing to go that far yet. All right, is everybody in that wants to get in? Let's get crack-a-lackin'. Good.
Mm-mm. Yes.
Good, because your thought process is, okay, well, what's the charge on an electron? It's negative. If I gain an extra, electron or two, then I'm going to have to become more negative, because now the electrons outweigh the number of protons. Good. Okay, so unequal sharing means electrons will be at one end of the molecule more than the other. That creates positive and negative ends, and that is polarity of charge. So that's a polar covalent bond. They're shared, but shared unequally. You got to watch the dogs. Good. Density. It's the only, mass has somewhat to do with it, but density is not mass. All righty. Good, 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 good. Stored energy is potential energy. Good. Catabolic. Anabolic means to bring together, so we would be creating bonds. All right, very good. Let's see who's the winner. Dun, dun, I think it's Levi. Here we go. All righty. Nicely done. Get out of there. Okay. So we're going to go back. Oh yeah, that's what it's called, the chat page. I don't know why I couldn't remember that. So I don't, if you need, you guys can chat between yourselves. If you have a question, unmute yourself and ask a question, because if I go back and forth too much and toggle, I'll lose the share and bad things happen after that. So, okay. So let's go back to our PowerPoint. All right. So hopefully I received. Now we're going to move into, so we have kind of the basis of chemistry, the subatomic particles. We know there's different bond types, there's different types of reactions. Now we're going to start kind of using that, talking about organic and inorganic molecules, so to speak. All right. So inorganic molecules, do not have both carbon and hydrogen. They usually dissociate in water, forming ions. Examples are water, oxygen, carbon dioxide, different gases, and other inorganic salts like sodium chloride. Organic molecules have at least carbon and hydrogen. Now, they frequently have oxygen, phosphorus, sulfur, nitrogen. There's all these other molecules that could be there, but to be organic, you have to at least have carbon and hydrogen. Right? Carbohydrates, proteins, lipids, and nucleic acids are the organic families we find in the body. And so we're going to be looking at those. So water, of the inorganic substances, water is the most abundant compound in living material. It is the major solvent of our body and in our body fluids. So we relate a lot of things to water and being polar covalently bonded. It's very, very good functionally to absorb and transport heat in the body as well. Oxygen is required to release energy from nutrients and metabolic activities. So when we start looking at cells briefly, we're going to talk about the mitochondria. In AMP2, we really look at how cells break down substrates using oxygen and burn it and produce ATP, which is what's called the energy currency of the cell. And oxygen is required for that. So we'll look at that more a little bit when we get to the cell chapter. Not much. We're just going to talk a little bit about the mitochondria, but we look at it in more detail when we talk about digestion and we look at metabolism. Carbon dioxide. Carbon dioxide is a product of burning those sugars and those molecules as energy in our mitochondria, actually. You go through 4 major phases of rearranging. The preferred molecule is glucose, but we could use other monosaccharides and disaccharides and proteins and fats for energy. It just is a different, slightly different pathway, but as a consequence of forming this ATP, we produce carbon dioxide. And that's where the carbon dioxide comes from that we have to exhale. Right? So what we'll learn in AMP2 is that if we have an abundance, it's normal to have a certain amount of carbon dioxide because everything is sort of in normal ranges in the body. And the normal range for carbon dioxide is 35 to 45 millimeters of mercury, in blood. If carbon dioxide starts to go up too high, carbon dioxide interacts with water to produce what's called carbonic acid, and it further breaks down into what's called hydrogen ions, which then contributes to altering dramatically the pH of your blood. So in AMP2, I love doing that stuff because that's kind of my favorite things, just to work at the acid-base balance stuff. Carbon dioxide is essentially a waste product, and it's a toxin, and thus it needs to be transported to the lungs. And you need to respirate, take a breath in, exhale it. You're taking air in to gain oxygen, but you primarily want to exhale and get rid of your carbon dioxide, and it must be removed from the body. It has a normal level in plasma, in blood, but you don't want it to build up because of the overall long-term effect it can have on altering your blood pH and creating an acidic environment. And thus we said, if pH values decrease too much, it denatures our proteins and breaks their hydrogen bonds. But we do more of that in AMP2. Inorganic salts are abundant in body fluids. They're sources of necessary ions. Oh gosh, we'll get into all kinds: sodium, chloride, potassium, calcium, hydrogen ions, bicarbonate ions, all different kinds of ions. Electrolytes, acids, and bases. So essentially, an electrolyte is an ion in solution. That's all. We were talking about the sodium chloride, the salt, the table salt, and we said, by itself in a box or a container or a salt shaker, it just has each other and it stays, in a crystalline form. But if I sprinkle it in water or on food, which is, like let's say, proteins, or like a burger or anything that you're eating, with the exception of that, there's water in there, and so it's going to dissolve in water. And so that's what electrolyte is ion in solution. Then we have acids and bases. Acids are any substance that put into solution, water generally, is going to break apart and dissociate and release H pluses. Those are hydrogen ions. Right. So HCl, hydrochloric acid, is called hydrochloric chloride acid because if we put it in water, it will, just like kind of like the salt did. You have something that has a positive and negative charge. The hydrogen in that HCl molecule is the positive and chlorine is the negative. If we put it just like we did with the salt in an environment, in another solvent, they break apart as well, because the hydrogen's like, I don't need this chlorine anymore. I can be attracted to, and create a hydrogen bond sort of with, the negative end of a water molecule. And I'm going to do that. And when it becomes free floating, sort of like that, as a hydrogen ion, that affects the pH of the solvent or the fluid that you're looking at. Bases are substances that can liberate hydroxide ions. All right. So down below we have sodium hydroxide, Na, and then an OH. We put that into solution in water, and it too, again, will break apart. It ionizes, right? It releases a sodium, but more importantly, it releases an OH negative. So the H pluses here from acids and the OH negatives from a base, can cancel each other out. If we have equal numbers of H pluses and OH negatives, it's just like having the same number of protons and electrons when we start, they cancel each other out and it's neutral. Well, this is the basis for the pH scale, all right? This picture just lets you see how if we have sodium chloride, we put it in water, which are the red and the two blue ball molecules, that they will break apart and how they will be suspended in water. Okay, so that takes us to acid and base concentration. I love this picture because, I gain a lot from reading, and I have pretty good reading comprehension skills, I will say, but I sometimes don't develop really good visual or kind of mental pictures to stay with me. And sometimes really good visual pictures stick with you longer than, having read text and trying to just memorize that, especially when you had pages and pages of notes. So pictures, I find, can be really, really helpful with really getting the point across and really like breaking down what this one image is trying to tell you that is also put in, words next to it. Right. So this blue-red model here represents the pH scale. Right? The pH scale indicates the concentration of hydrogen ions in the solution. Technically, it's the relationship of hydrogen ions to hydroxide ions. Right? But we often refer to the hydrogen ion concentration increasing or decreasing because the way we check the pH of a solution is using something like litmus paper. And litmus paper is responding to the H pluses, not the OH negatives. But we know that that value associated, to a solution is based on the ratio of H pluses to OH negatives. Okay, so let's kind of look at this scale. The scale is on the bottom, right? We have a scale of 0 to 14, all right? And in the middle is 7, all right? We have the red area that represents hydrogen ions and the blue area that represents hydroxide ions. So let's just start at neutral because I think that's the easiest. All right. Here, the red area equals the blue area, which means the hydrogen ions, let's say there's 45 of them. We have 45 hydrogen ions, 45 hydroxide ions. The reds plus, the plus items equals the negative hydroxide ions. And therefore they cancel each other out, and that's what makes them neutral. All right. So right there, like, okay, when the H plus is equal to OH negatives, it's a neutral solution. That's what 7 is for. Now, let's say we move to the right and we go from a value of 7 to 8 to 9 and 10. Look up at the top. The area of red is getting smaller and the blue is getting larger. So as the hydrogens decrease and the hydroxides are actually increasing, the pH value we're assigning to that solution is increasing. It's increasing. If we start, if we're at 9 and the hydrogen ion concentration decreases, which means the hydroxide concentration is increasing, the pH value may become 10 or go up to 11 or 13 or 14 even. It depends how much they change, right? So as the hydrogens decrease, the pH value increases, and vice versa, right? As the hydrogen ion concentration increases, the pH value we assign to the solution decreases. So let's go back to, or let's go to 10, all right? Where we have mostly hydroxide ions in blue and fewer in, hydrogen ions in red. If the hydrogen ion concentration increases, it essentially, displaces the number of hydroxide ions, right? And that we might move from a pH from 10 to now 9 or 8, 7, 6, maybe all the way down to 3. Right now, I look at pH value of 3, we have way more hydrogen ions than hydroxide ions. So as the red area gets larger and broader because the number of hydrogen ions are increasing and the OH negatives are decreasing, the pH value we assign to the solution is diminishing, is decreasing. right? And that's because pH value is based on what's called the negative logarithmic of the hydrogen ion concentration. Yeah, for the, you chemistry people, right? What does that mean? The negative logarithmic means that as the concentration of hydrogen ions goes up, the value we're associating, we're going to assign is decreasing. If the pH was based, equaled the positive, just the logarithmic concentration of hydrogen ions, it would mean that as the hydrogen ion concentration increased, the value associated, we would assign to it would be increasing, but it's not, it's a negative logarithmic. All right, so as hydrogen ions go up, pH value goes down, period. Right, and tattoo that on your ankle. All right, so acidic, right, the acidic region of a pH scale is that region less than 7 and between 0. Actually, the pH scale goes less than 0 now, but we won't even get into that. So less than neutral, less than 7, 6.99999920 technically is the acid end of the scale. And anything in excess of 7 up to 14 would be the alkaline or base end. The farther you get to the extreme ends, like toward 13 and 14 or 1 and 2, the stronger the acid is or the stronger the base is, and they are just as toxic and lethal in the body. Your normal pH of blood is 7.35 to 7.45, and you can only survive 6.8 to 8.0. So, things that are way up here in the alkaline scale, like ammonia, and bleach, you don't fare so well when you drink that stuff, do you? No, you don't. It also has organic components in it that are very burning and toxic, but part of it is because it's a very strong base and it can dramatically alter your pH. So although we don't normally have a lot of opportunities at all where the pH is really high in blood, certain toxicities, with children and things ingesting, different fluids maybe that they can get their hands on. That's why you have to lock everything up with them, that's how it can be, become lethal, is that you have things that are very strong, acids, which generally burn more. If you think about the bases like that are extreme, ammonia and bleaches, they kind of burn after a while, but they're more kind of slippery kind of a texture on your hands. They don't have the same noxious reaction stimulus. If someone went to drink it, especially a child, they would just swallow it, and then all of a sudden later they'd be like, oh God. But acids are generally, kind of burn on contact. They're a little less likely, to be ingested. But anyway, here we have the scale on a vertical axis, and we see common household items that fall into those pH ranges. They're just kind of interesting to see. And it gives you actually over to the left-hand side, the concentration moles per liter of hydroxide ions to hydrogen ions and how they change, for those people who want to know. Okay. Neutralization and buffers. Buffers act as acids when the pH is high and bases when the pH is low to stabilize the pH of a solution. So buffers, in every area of the body, there's an optimal pH range, as I described before, optimal pH and temperature that tissues and cells like to live at. And that's true of viruses, as we well know now, and bacteria as well. So buffers help maintain a stable pH in an area. And if the pH is really high, in the case of in the upper, alkaline range, then we want that buffer to act as an acid so it can interact with that alkaline or that OH molecule and decrease the pH so that it comes back into a normal range. And if we're on the acid end of the scale, then the buffer acts as the buffer acts as an alkaline molecule, like an OH negative, and it'll interact with the hydrogen ions to kind of form water and thus decrease the hydrogen ion concentration and increase the pH value. Right. So buffers, are trying to manipulate that ratio of hydrogen to hydroxide ion to keep and stabilize a pH. Okay, so now we're going to talk about our 4 organic families of the body. And we're going to look at, what their building blocks are, what their intermediate molecules are, if they have one, their macromolecules, what kind of bond type or what's the primary bond type and what some functions are. And this, especially if you're taking AMP1 lab on this campus as a Gibbs lab, it probably has a lot of that in it, especially if you have maybe Dr. Brightman. Mrs. Weiser isn't teaching this summer, but Dr. Byrne is teaching also. He does a lot of this as well. Okay, because you're going to put it kind of in a chart form, and I'll show you where that chart is that I put up for you. Okay, so carbohydrates. All carbohydrates, the building blocks, intermediate macromolecules, polar covalently bonded. Right? The building blocks are called monosaccharides. Mono means one, and saccharide means sugar. Of our monosaccharides, we had glu, fru, gal, glucose, fructose, and galactose. And technically, ribose is a building block. And this will make more sense when we look at DNA and RNA, because DNA means deoxyribonucleic acid, and then we have ribonucleic acids, and that ribose stands for the ribose, and thus it's part of the reason why those molecules will be polar covalently bonded, as well as it will then let you see exactly where these hydrogen bonds will be located, because we'll have multiple polar covalently bonded molecules. All right, so the building blocks are glu, fru, gal, glucose, fructose, and galactose. And its function, monosaccharides function as quick energy. Glucose is the preferred molecule in cellular respiration. Cells like to have glucose to convert to ATP in its mitochondria. Loves it. Right, we put a couple of those together, we get the intermediate molecule of a disaccharide, which is two sugars. And those are sucmol-lac, sucrose, maltose, lactose. Sucrose, maltose, lactose. Each disaccharide is made up of at least one glucose and maybe a fructose, or two glucoses, or a glucose and a galactose. I don't require you to know that in AMP1. You're going to go back over that in the digestive system, the chemical digestion chapter of AMP2. And then we have macromolecules, which are the polysaccharides, many sugars, glycogen and cellulose / starch. Glycogen is the storage form of the polysaccharides in humans or in animals, and starch is the storage form in plants. Polysaccharides function as short-term energy storage, because when we have, and we've been taking in excess carbohydrates, all right, our glucose levels are, our blood glucose levels are elevating, and we signal with insulin that your body cells take up glucose now because it's abundant in the body and it's higher than normal. And when that is sort of filled up and stored in in the cells, then it signals skeletal muscle and the liver to do the same thing. So they'll take those glucose molecules and they will hydrolytically, or they'll, using dehydration synthesis, is put them in a long polysaccharide chain called glycogen. And that's how they store it for later. When your blood glucose levels fall later, or should they fall, then we secrete another hormone called glycogen, and that stimulates the liver to break down that glycogen into the little building blocks of the monosaccharides, the glucose, and put it back in the blood, because now we need some more glucose. So that's why it's considered short-term energy storage. Your muscles use it when the muscles start to work, because that's going to be a nice close energy source for working muscles. But it doesn't usually last long. Long-term energy storage is going to be fat, like get stuck on your butt and on your abdomen, fat. All right, so you should be familiar with what mono, di, and poly mean, and what saccharide means, which is sugar. And that glycogen, is the storage form of carbs. It's the short-term energy storage. Quick energy are your building blocks. Like to ask that in lab sometimes. I do. And this is what, the individual green kind of hexagonal shape there would be one, monosaccharide. You put them in chains and you have things like glycogen. All right, then we move on to proteins. Proteins are a little more complicated. They have a little more extra stuff to kind of know about it. And it is the most complicated, I would say, and sophisticated organic family in the body? Well, first of all, proteins are polar covalently bonded as well. No shocker there, because water is polar covalently bonded. The building blocks are called amino acids. Intermediate molecules are called dipeptides. And the long chains, the macromolecules, are called polypeptides. And an example of a polypeptide is albumin. We have 20 different types of amino acids to build more complex proteins. Proteins are susceptible to denaturation, which occurs in low pH and high temperatures. So before, when we were talking about the chemical reactions, we said the enzymes were composed of proteins. This is part of this, proteins form all these molecules and structures that have very sophisticated, unique, and complicated functions. Carbohydrates don't do it, and neither do fats. Right? So these proteins, like we said before, that can form enzymes as well. When it comes to chemical reactions, if we increase the temperature of the reaction, there's a point where we start to disrupt and kind of cook up our enzymes, and if the pH goes too low, and that's because that causes what's called denaturation in our proteins. Denaturation means you're breaking your hydrogen bonds, essentially. So proteins are very susceptible to that. Okay, so functions of proteins: it forms hair, nails, muscles, hormones, receptors, enzymes, antibodies, and albumin. Albumin in plasma helps maintain what's called an osmotic gradient. And we'll get into that a little bit more, when we look at cells, and even more, in AMP2. But look at all the different types of function, and that's not all of them. Those are just some examples. So look at the variety of types of structures that we're looking at. Receptors to the inside or the outside of the membrane, of a cellular membrane, antibodies, that are very unique. They are their bonding sites, are like a lock and key relationship, very specific. Enzymes, hormones. Hormones can either be, more protein, carbohydrate, protein and some carbohydrate, or kind of fat-based. Amino acids are held together with polar covalent bonds, and it's also when they occur in proteins, they're sometimes referred to as just peptide bonds. Right. So lots of variety, lots of levels of sophistication. Well, we're going to show you in just a minute how that can be acquired, given its primary, secondary, tertiary, and quaternary structure. This is the picture I was kind of sort of alluding to when we were talking about how enzymes work. We said that enzymes will often have binding sites for specific molecules or reactants, substrates in a chemical reaction. And only a certain molecule can fit in there. Sometimes they're two identical, let's say in this case, amino acids, but they could be two different amino acids. Right? And once they are able to, be captured by this enzyme, the enzyme essentially puts them together. It facilitates dehydration synthesis. So here, we go from that, E to number 1, and then number 2, the ES complex undergoes internal rearrangements that produce the product. Look, you can see a water molecule being released. Energy is being stored, creating a bond, right? Dehydration synthesis. And then when it's done, the enzyme just releases the product. So the more enzymes you had, and of course, the more substrates, the amino acids available in the environment, the quicker, the faster you can release your product. And that's why they increase, the chemical reactions, and what's called lower the activation energy. Okay, so proteins, we have 4 levels of protein structure, and we said we had 20 different types of amino acids. So my analogy is, picture a box that has 20 different colored beads, that you can put on a string. Your primary sequence is the, let's say, 100 beads that you can put on a string. And you can choose any combination you like of the beads that are in that box. You can have them all alternating. You can have, 2 white and the red and the yellow, purple, green, fuchsia, whatever. Right. That first sequence, of the 20 amino acids available to you is its primary structure. All right, then, given that each individual bead is polar covalently bonded, it means each individual bead has a positive and negative end to it, correct? Because that's the definition of a polar covalent bond, right? Right. So each of these beads in this primary structure, has positive and negative ends to it. And when it's just linear in its primary structure, you're like, okay, it doesn't really have anything to really bind to. We just have one amino acid to another. But what if we kink it? What if we take that long string and sort of like having, if you had literally a piece of string in your fingers and you're holding it vertically and you dropped it on your desk, the string would kind of coil on itself, wouldn't it? Unless the wind's blowing, right? So where areas of where one amino acid comes close to another, the positive end of one amino acid is going to end up being attracted to the negative end of the other amino acid that has now come close to it. And if it thus forms a pleat, like here on the bottom, a beta pleat, or over to the right, a helix, right? That shape of a helix or a beta pleat is maintained because the positive negative ends of these amino acids that get close to each other form a hydrogen bond. All right. So what maintains this secondary structure, and over here on the right, you can kind of see where the red little bonds are located. They have these little red dots. And between, let's say, right in the middle, you have a hydrogen to a nitrogen and another hydrogen to a nitrogen. Right? That means that the positive end of one is being attracted to the negative end of the other, and it keeps that fold or that kink, right? And that's a hydrogen bond. Right? So now maybe we have this long spiral, which is its secondary structure. Now we can take that and let's say tie it in a knot, like in the shape of a pretzel. Well, the same hydrogen bonds that maintained that secondary structure is now going to maintain this tertiary structure. So now you've taken that long coil and you've tied it in a knot. Well, what keeps that knot in place? Again, the positive end of one amino acid being now developing a hydrogen bond somewhere down that helix to another negative end of an amino acid, and so forth and so on. Again, the hydrogen bonds are weak-ish, but they work really well. Right? So now we've gone from a single strand to maybe a helix, and now kind of a knot, like a pretzel. Right? That's its tertiary structure. But it gets better because there's more. Now we can take maybe multiple tertiary structures, a couple pretzels, and bind them together and approximate them. And again, for the same reasons that we maintain the tertiary and secondary structure, negative ends at one end of one of those tertiary molecules will be attracted to the negative end of another tertiary molecule, and where internal, like belly region, so to speak, of that approach another one, they then become hydrogen bonding between multiple tertiary structures. And that forms its fourth level called the quaternary structure. Right, so once we get beyond the primary sequence and structure here, the secondary, tertiary, and quaternary structures are maintained in that shape and don't just unravel back to its primary because you had these hydrogen bonds. That's an example of intramolecular hydrogen bonding. Proteins are a prime example. And this is why this level of sophistication, keep in mind, is that let's say we have a protein that has 100 amino acids, or maybe even 200 amino acids in its primary structure. Whenever you change even one amino acid, it can change maybe not the entire molecule, but generally certain characteristics of that molecule, certain behaviors of that molecule, let's say. So just changing 1 out of 200 can really change that molecule. And that's just the primary structure. Then we can change a secondary structure to maybe even being a helix or a beta pleat, and then we can change it into how many, like a tertiary structure. And then the quaternary structure maybe just has 2 tertiaries, or maybe it has 4 tertiaries, like hemoglobin and red blood cells. That lends it to have all these different combinations, that can be produced. And that's why proteins can be so specific, and they are so specific. However, they're very vulnerable to fever in the body, to acidic conditions, in blood. That's why fever is so, you have to control, increased body temperature in the body, because you will start to break the quaternary structures, the tertiary structures, everything just starts to unravel. And then you just end up sort of with either, at best, a secondary structure. You might just end up with a primary structure. It just falls apart. It just unravels completely. So that is unique for proteins. They're the only organic family that has that. That allows them to function as hair and immunoglobulins and protein, receptors and enzymes and hormones. It allows you to have all this sophisticated functioning molecules. Okay, then we move on to lipids. We're getting closer to the end, right? Lipids are non-polar covalently bonded, so they are insoluble in water. All right, is the only family of non-polar covalent bonds. A neutral fat is called a triglyceride. Triglycerides function as long-term energy storage. Don't we know it, right? It's kind of hard to burn fat. And they act to cushion and insulate organs forever and forever. The building blocks are 1 glycerol and 3 fatty acids. And thankfully, for the last couple organic families here, we go from a building block right to a macromolecule. So that macromolecule is a triglyceride. The model is on the bottom. So the 3 carbon chain over here, that's vertical in the darker kind of tan color, that is the glycerol portion. It's a 3 carbon chain. And attached to each carbon is this tail, this chain of carbons with hydrogens attached to them. And each one of those is called a fatty acid tail or a fatty acid. So that is our triglyceride. 1 glycerol and 3 fatty acids are the building blocks. Phospholipids are what's called a modified triglyceride. Phospholipids, if we take a phospholipid, let's look it down on the bottom because I think this will speak more volumes. On the bottom there, we have 1 triglyceride. We have the 3 carbon chain vertically, and attached to each carbon, we have a fatty acid tail. All right, that's a triglyceride. If I take off one of those fatty acid tails and I swap out a phosphate group, now that molecule becomes a phospholipid, all right, a phospholipid. And then further to the right, C is the symbol they usually use in most diagrams of a phospholipid. It has a little round ball and 2 tails representing the 2 fatty acid tails that are part of this molecule. Right. So the building blocks of a phospholipid, right, is 1 glycerol, 2 fatty acids, right, like a lipid, but instead of having 3 fatty acids, we're going to have 1 phosphate group. So we had the same glycerol backbone, 2 fatty acids, and a phosphate group. The macromolecule form is called a phospholipid. Where do we, what do phospholipids do? We're going to look at that in the cell chapter. These are the building blocks or the components of plasma membranes or a cell membrane. It's also what forms the membrane around organelles within the cell. So they're going to have that same kind of ball with 2 little tails. What's the primary bond type? They are the combo pack of polar and non-polar covalently bonded molecules. And let me just explain this to you. Of the building blocks, those portions that are same as a triglyceride, the glycerol and the 2 fatty acids, that is going to be the non-polar covalent parts of that molecule. But the phosphate group is polar covalently bonded. All right, so parts of that molecule where the tails are non-polar covalently bonded. Where the ball is, we have polar covalent bonds. Therefore, the tails are what's called the hydrophobic ends of the molecule. Right? They dislike water. Why? Because they have incompatible bond types. Right? The phosphate end is the hydrophilic end. It likes water. Why? Because it's polar covalently bonded just like water. Right? So this molecule and these molecules are going to orient themselves to form a plasma membrane, that the fatty acid tails will point toward each other and the balls, the phosphate groups, stick outward, and will be, in contact with the extracellular fluid and the intercellular fluid, because they like being bonded with them. They have similar bond types. And this will make a little bit more sense when we actually see, the model of the cell. Right. But right now, you just need to know the phospholipid, right? What the building blocks are, the macromolecule form, what are their bond types, what does it mean to be hydrophobic and hydrophilic, and then, its function as a component of the cell membrane. If we look to see how similar it is to a triglyceride, it makes a little more sense. Okay, so other lipids are things like steroids and cholesterols. Steroids kind of look like 4 stop signs welded together. That's down the bottom to the left-hand side, A, the general structure of a steroid. We find these embedded between the fatty acid tails in a plasma membrane because it gives that membrane a little support. It gives a little bit of rigidity without being totally firm. And that way, when you have one cell adjacent to another to try to find, form a type of adhesion, the cell wall isn't just kind of moving back and forth. It gives it a little bit of firmness to it. So they are the 4 connective rings, of carbon, widely distributed in the body with various functions. It is a component of a cell membrane. We'll see it in one of the images, of a cell membrane in the next chapter. It's also used to synthesize hormones, so steroid hormones like estrogen, progesterone, testosterone. And it can also is the basis of forming cholesterol. Essentially you have a steroid molecule over here on the right with a chain of carbons and some hydrogens attached to them. And that's what a cholesterol is. All in the same family, all nonpolar covalently bonded. Last family are our nucleic acids. They function to carry genetic material or store it there. They encode for amino acid sequences of proteins, what I call the recipe book for making all those proteins, because, it's very specific, out of, how many 20 different amino acids, and you might require a chain of 120 or 90 amino acids. You better know what you're doing. You have to have the recipe just right. It needs to be put in its primary, sequence appropriately. Then it needs to be modified into its appropriate secondary, tertiary, and even quaternary structure. So the book, the recipe of how to do that is maintained in DNA. DNA stays in the nucleus until the cell is dividing. If we need to get a copy of that recipe, we're going to unzip the DNA. We're going to use RNA to kind of make a photocopy. RNA detaches and it takes the recipe from the nucleus out into the cytoplasm so that the ribosomes can now read the recipe and make proteins. Okay, so the bond type is primarily polar covalent bonds because of so much ribose, the sugar within it. But I will tell you that in the center of DNA, we have hydrogen bonds. The building blocks of nucleic acids are called nucleotides. And the macromolecules are DNA and RNA. So we don't have an intermediate product or intermediate molecule. DNA stands for deoxyribonucleic acid. This is our double helix, and RNA is ribonucleic acid, a single helix. Okay, and this just shows you, essentially, let me just move this over, where if we had DNA, the hydrogen bonds are right through the center of the helix where we have what's called nitrogenous base pairing. There are certain nitrogenous bases that will always bind together in DNA and RNA. It has to do with really how many bonds they're capable of forming between A for adenine and T for thymine. You form 2 hydrogen bonds, and then between cytosine and guanine in DNA, we form 3 bonds. So there's specific, bonds and lining up of what's called nitrogenous base pairs in DNA. And in RNA, it's rather similar, except for instead of having thymine, we only have uracil. But, we're not going to get into that because it's not a bio class. But right through the center here is where we have hydrogen bonds. And this kind of makes sense too. Covalent bonds, polar or nonpolar, are, pretty damn strong bonds. And we have lots of sugars along that backbone, because on the backbone where you have those pink and purple kind of stripes, it shows you there, or it indicates sugar phosphate backbone. Remember, we just said phosphate was polar covalently bonded as well, and sugars are polar covalently bonded. So you want the backbone. It's sort of like unzipping a zipper. When you unzip a zipper, you want in the center the teeth to come apart, but you don't want the sides of the fabric that forms the zipper, whatever it's attaching to unravel, do you? You want to be able to close it up to the center and unzip it from top to bottom or bottom to top. All right. So all you want to do, think of DNA as being a zipper like that, except it's in a helix. It's twisted. You unzip it in the middle and then you re-zip it back up again. Why? Because hydrogen bonds are rather weak. And this works to your advantage because when you need to copy your DNA, you quick unzip it and then re-zip it back again. Or in the case of copying it, you're just going to rematch and make two copies essentially. But let's say you want to, make a new protein or replace some proteins. You unzip and then re-zip back. And it can do that because of the hydrogen bonds in the center. Okay, adenosine triphosphate or ATP, we're going to hear that a lot. This is a large molecule that has 3 phosphate groups attached. And the last phosphate group from the one at the end to the one in the middle, that bond has the highest energy, within that molecule. And when that is broken, it releases a lot of energy to perform work that has to occur, in the cell. And there's all kinds of work that's being done by a cell. I mean, it kind of depends on the cell. For instance, white blood cells actively, what's called phagocytize, engulf bacteria and viruses and things, and then it has to use one of its lysosomes to merge with it and release these digestive enzymes to break it down, to kill off the bacteria, the virus, or even the parasite. Right? And that costs money, that takes energy. It's like any pump in your house for air conditioning or heat or running your car, any kind of pump or moving something against the concentration gradient, requires money, and money in a cell is in the form of ATP. So the mitochondria like to take those glucose molecules, and then it uses oxygen to rearrange multiple ways, this glucose molecule, and produce about 32, to 36 ATP. And that ATP, every time you have a pump, boom, ATP. Every time you have, myosin connecting with actin, when it comes to muscle contraction, every ratchet, every contact in what's called the power stroke, ATP. Our cells need a lot of ATP. And that's why we eat food. It's not, now we eat most food because of taste, and some of us eat more food than we actually need. But food and oxygen is so our cells have something to burn so it can perform all its functions. And without the food, everything just starts to die. When glucose is broken down in a cell, it produces many molecules of ATP to pay for pumps and muscle contraction and enzymes that have to work and grab things and put them together. It all costs money, baby. So that's where it's coming from. Okay, so that takes us to, oops, someone's dog is barking. Let's go to the next Kahoot. I'm going to stop my share and then reshare in just a second. Maybe it doesn't seem to be working right now. Hold on. Let me try it again. Oh, there it is. Okay, now I got to toggle around a little bit. Hang out there just for a second. Here we go. Ta-ta. Caitlin's back. All right. All right, at least good. Here, we'll try some other music. Hold on there. We can do disco. So those of you who are signing into the Kahoot, remember when you come in is try to turn on, you don't have to keep your camera all the time and you really don't have to, but it would be really, to develop a community here of faces and people, and you don't have to be dressed up or anything, but, if you could turn your camera on periodically and stuff, it's just nice where I can actually see a face instead of just talking to my screen here by myself. All right, is everybody in that wants to get in? Okay. Ooh, okay, so remember, and you were, close in green. It should have been a dipeptide, not a peptide, but otherwise, you're very, very close. Good. We'll look at the winners at the end. Good. Need to get that a little bit better, but pretty good. That's 3. All right. Dehydration synthesis. Dehydrate means to remove water. So you had to been in the title someplace. You put things together, or you put molecules together, and you create bonds, and you store energy in those bonds. She was in her class. All right, water is not organic. To be organic, you have to have carbon and hydrogen. Water is H2O. Good. Lots of sugar, lots of phosphate. Nice. And then you go, okay, what would they be? Glucose, fructose, galactose. And then you go to the disaccharides. All right, that's the intermediate, sucrose, maltose, lactose. Nice. Very good. Who said an atom's nucleus? I think you hit the wrong one. That was a mistake. This is a good question. Good. Bond type, we need to know, do you have compatible or incompatible bond types? And size, the smaller you are, the easier it is to suspend. The larger it is, not that it won't be soluble, but it won't be highly soluble. It'll be maybe moderately or low solubility. Good. All right, good. Well, at least no one chose blue, the mood or the appetite. That was good. You'll get used to these after a while. If you look at them and you really kind of think about what they're referring to, or which variable, so to speak, what effect it would have, it'll stick with you a little bit longer. Okay, good. We'll see the results. Very good. Okay, let me stop my share here. And all right, so that is the end of the notes. I'm going to, let me get back in here for a second. Okay, let me just shrink this for a minute. I just want to close out my notes and get into the course page. Oh, there are the puppies. All right, we're gonna. Okay, so what I'm going to do is I'm going to change my share to my course page so you can see where that chemistry chart is located. So hold on, I'm gonna go this way and then gonna open it up temporarily. Okay, so let's go to course content and go to exam 1 notes. So now we've talked about chemistry, which was the PowerPoint we just looked at. Here's your quiz. Here's your chemistry chart for EMP1. All right, so I'm going to open that up. And let me download it because I think I can turn it around that way. All right, okay, well, in any event, yeah, actually I can. Hold on, let me just move this out of the way. Let me open this. I might have to change the share again, unfortunately. It helped, but not too much. Okay, let me just go back. Change this, hold on. Okay, so this is sideways because that's the way it scanned it. Let me see, let me do it this so I can rotate, I think. Okay, that's better. All right, so this is my really bad handwriting. This is why I don't do this that much anymore. All right, so, if we want to, and this really seems to help people organize, especially all that organic families, bond types and functions and so forth, and puts it in a useful, I think, visual, organized pattern, so to speak. On the top, we have our 4 families: carbohydrates, proteins, lipids, and nucleic acids. And by the way, usually in a face-to-face class, I do this on the board, and then we just kind of, you can copy it as I do it or afterwards, or do it or don't do it. But generally students find this to be helpful. Okay, and then on the vertical axis over to the left, we have building blocks all the way across, right? Intermediate molecules, macromolecules, primary bond type, right? And then we write in some functions here and there. Okay, so what I do is I color code each family, right? So carbohydrates, I had in this kind of a fuchsia color. So the building blocks of a carbohydrate are monosaccharides, and they're in a little block there. Glufrugal, and you can write ribose in there if you want also, right? So glucose, fructose, galactose. Functions as quick energy. People like to ask you the difference between quick energy, short-term energy storage, long-term energy storage, especially in lab here. Okay, then we have the intermediate form of carbohydrate is your disaccharide, sucmalak. The macromolecule is a polysaccharide. In humans, it's glycogen. In plants, it's starch. Functions as short-term energy storage. And the primary bond type is polar covalent. Polar covalent. I don't think there's anything else on the bottom. The function I put as a star because I put the two functions right there, or an asterisk. All right, then proteins, building blocks, amino acids, intermediate molecule, dipeptide, macromolecule, polypeptide. What's kind of unique about it? The two stars here, it has a primary, secondary, tertiary, and quaternary structure. Ding, ding, ding. I'm pretty certain you're going to get a question on an exam about that. Which family demonstrates a primary, secondary, tertiary, and quaternary structure? Because it's unique to proteins. I mean, what allows proteins to have all these functions. The primary bond type is polar covalent. Albumin is a protein that has, we like you to know this particular function, maintains an osmotic gradient, because we use this a lot in AMP2. But proteins also form hair, nails, enzymes, antibodies, receptors. The list goes on. Right, then we get to the left, we look at lipids in blue. Right, we have one glycerol and 3 fatty acids. Those are the building blocks of the macromolecule of a triglyceride. Other examples of macromolecules in the lipid family are steroids and cholesterols. So down here in blue, they are non-polar covalently bonded, and they function as long-term energy storage, cushion, and insulate organs. Just to the right of it, this is where we have our modified triglyceride. This is going to be our phospholipid. So in this building block, we have one glycerol, 2 fatty acids, and 1 phosphate group. Right. That forms the macromolecule, the phospholipid below it. Right. The 1 glycerol and 2 fatty acids is the hydrophobic group. Thus, that must be the nonpolar covalently bonded end. And the phosphate group is the hydrophilic end. That is the polar covalently bonded end. Right. So the primary bond type is both polar and nonpolar bonds, and functionally it forms the plasma membrane and vesicles and things like that. Right. Then the last category are nucleic acids, the building blocks of nucleotides. The macromolecule is DNA and RNA. The primary bond type is polar covalent. If you want to know, yes, through the center of DNA there are hydrogen bonds, that's fine. That's fine. But the primary bond type is polar covalent because you have to be polar covalently bonded first to have hydrogen bonds. And functions to store genetic material and instructions for protein synthesis, the recipe for all the proteins of the cell. So hopefully that helps you kind of organize that part. You still have to kind of go back through, and I do like chemistry, I have to tell you, there are a lot of questions that come from chemistry because you have to know what are protons, neutrons, and electrons. What's a dehydration synthesis reaction versus hydrolysis? What are some of these building blocks? What would be, what is unique about it? What are some of the functions? You kind of get this over time as well. It comes back again in the digestion chapter, in AMP2. But I think this is something, again, if you purchase, a whiteboard of some kind, and you can get these at Home Depot. I don't know if I mentioned that to you before, but the whiteboards we have, like in the different classrooms, you can get big sheets like that cut to whatever size you want in Home Depot. And you can get a big, like 6 feet by 3 feet, for, I don't know, $5–10. And then you can kind of drill holes in it and just hang it up with carabiners or something, and you've got like a wall of whiteboard you can use, and just buy your own expos and just clean it regularly, and you can practice drawing over and over and over again, because Really, anatomy and physiology is memorization and repetition. There's physiology in there. There's more really in AMP2, but AMP1 is rotely and repetitiously going through it over and over again until you get it drilled in your head. And then you have this epiphany of how it's all interrelated to one another. And you keep having those epiphanies kind of throughout your lifetime, when it comes back to a lot of these sciences. But this should be, I've been told, I think it's a really good tool for organizing and learning this. You can start by just doing the headings and just practice the carbohydrates, and then do carbohydrates and proteins, and then just do, maybe the lipids, the phospholipids and nucleic acids, and then do them all together, and kind of practice recreating that as fast as you can. Okay, so that is the end of the material for tonight. Does anybody have any questions? Nobody wants to. I know it's kind of tiresome. It's a long lecture, but if you have a question, just shoot me an email. Quizzes are due, this weekend, so make sure you get those done.
I have a question.
Can you? Okay, who is it?
Janet Chanda.
Do you have your camera on? Can you turn on the camera? Where are you, lovey?
Wait, hold on.
Jeanette, is that who it is? Okay.
Yes. So you know how for the my course labs, we don't have any assignments to do in there, right?
No.
Okay. And then you were telling us to save something in a folder. I couldn't find it. I emailed you about it, and you say you couldn't understand my email.
Yeah, I don't understand the question now either. So start from the beginning. A folder. All right. Are you talking about where you find the notes?
Yes.
Okay. I'm going to show you right now. Hold on. Hold on. I'm coming. I'm going to share my page with you. So hold on. This. All right. Do you see where I'm at? I'm on the home course page.
Yes.
All right. So you have course home, which is this page. All right. And what I was saying here with accessing the study area is you can do that if you want. You get, if you purchased a book, or even if you purchased just the access code, you would click on one of these, and you can just play around and find some of the materials they have there, but no, there are no assignments there. All right, then you go to course content. All right. And this is where we have the syllabus, lecture schedule, my office hours, where you're going to find these Zooms stored, because I will, I will upload this Zoom. Right. Here you have your exam 1 notes, exam 2 notes. Did you navigate through here at all?
Yes.
Okay, so this is where the notes are. This is where you find the quizzes. And at the end of exam 1 notes, you have exam 1. And then
So we just have to do the quizzes, right?
So read the syllabus. I want you guys to, take this opportunity to read this stuff. All right, is that the syllabus tells you that you have quizzes and exams. They're all on the schedule, and they all have certain due dates. Right? Attendance is based on completing these things, and I will perform these Zooms and then upload them. In the event that you don't have the opportunity to, attend each one. I really take these attendance based on completing those quizzes and things. So, kind of look around in here and read through those, because it's not a long syllabus just for that reason. I want it to be concise so that you don't get too lost in that, so that way it's very clear what your responsibilities are. If you can use the calendar, which I suggest using our lecture schedule that tells you when your quizzes are due, and check them off as you go, or you can click on your calendar, and whatever I set mine on month to month, it tells you when our Zooms are and when your when your quizzes are due, and further when your exams are due, because the following exam is, the next week. So here we have on the 6th, this is exam 1 availability ends on week 4. So that is also a reminder of your different assignments. Does that answer your question?
Yes, ma'am. Thank you.
Okay, yeah, so, look around in there and read through the material that's put up there. So that way you're not, it's when you're just emailing like this, it can be kind of hard to communicate really what your question is sometimes, but I didn't, really gather that at all. But, zooming like this, it gives you an opportunity so that I can just literally, show you, the answer to your question. All right, very good. Anybody else? All right, well, if no one has any questions, I'm going to sign off. All right. And if you do have a question, shoot me an email, get your quizzes done by Sunday night, please, because that's their due date. The other quizzes for the next chapter are open as well if you want to work ahead. So, okay. All righty, then have a good weekend.
Thank
Thanks,
you.
Professor.
Bye.